speaking only for, it's on. Good afternoon, everybody. Welcome to today's Copy with Curiosity. February end, last week of February, is a time when everybody is busy. Students are busy preparing for their exams, and elders are busy with their schedules. They have got their own deadlines in offices and all. So it is really heartening to see so many of you here today, okay, on a Sunday afternoon for today's lecture. And welcome you all again. We at Jawaharlal Nehru Planetarium organize several programs for dissemination of science. Organizing popular lectures is one of them. We used to have these lectures off and on earlier also, occasionally. And with starting of Copy with Curiosity lecture series by ICTS and associating us to have those lectures here has given a very big boost to this program. And we are very happy with that. And in fact, this year, in 2018, till now, we have had 6 public lectures. So thanks to them. Now, I extend a very warm welcome to Professor Urbasi Sinha, today's speaker. A hearty welcome to you, madam. I request Professor Rajesh Gopakumar to speak a few words about ICTS. Thank you.
Hello. Yes, thank you, Dr. Pramod. And as he said, we have been embarking on this very fruitful partnership with the Planetarium from August 2016 onwards, October 2016 onwards, so nearly 1.5 years. And it's always very gratifying to come here on these Sunday afternoons and see so many bright, enthusiastic faces, all eager for science. I think I missed maybe only 1 or 2 because I was out of town, but it is really very something very inspiring. And I would like to thank all of you, many of you are regulars at this, and I'm very happy that you that you are coming. ICTS has as one of its mandates outreach. We try to organize several events. The Copy with Curiosity is our flagship outreach event. We also have public lectures and other events in our campus, which is in Hesarghata in North Bangalore. So we really take outreach very seriously. We would like to do many more things so that the Bangalore public gets enthused with science, and many of you will hopefully, those of you who are students in school or college will hopefully even turn to science as a career, inspired by some of the talks and events over here. That's one of the mandates of ICTS. We also do research, high-level research in a variety of areas, ranging from string theory, black holes, gravitational waves, to condensed matter physics and or solid-state physics, fluid dynamics, biophysics, and so on, and also in pure mathematics, pure and applied areas of mathematics, and possibly in computer science as we go along. So we have quite a wide canvas in our research. And the third component of ICTS's mandate is to organize programs and research workshops in frontier areas of science in many of the theoretical sciences. And we take that, of course, also very seriously. We act as a scientific hub for the Indian science community to come and organize events, long collaborative workshops and meetings where students can be exposed to some of the modern areas of research, and this has been very successful as well. All our lectures, including our past Kaapi with Kuriosity, other public lectures, we had Kip Thorne's lecture in January that is there. I think more than 10,000 people have already viewed it. If you haven't seen it, do go and watch it. But all the past Kaapi with Kuriosity, as well as many of the lectures in our, the more advanced lectures in our institute as part of the programs we organize. These are all available on our ICTS Talks YouTube channel. So if you go to YouTube and type in ICTS, you will get a web page. And if you really like the videos, you can subscribe and you will get notified of these events. Similarly, for some of our public events, you can sign up for a newsletter on our webpage. So that's what I wanted to say about ICTS. I'm really happy today that Urbasi has agreed to give this Kaapi with Kuriosity. It is a first in the sense that it's the first time we are having a live demo, and science is not just about lectures and talk, and today's will sort of really show you some very exciting, amazing physics phenomena right in front of your eyes. So I'm very glad that Kaapi with Kuriosity has taken this new turn as well, and I hope there will be more such demos in future lectures. So let me stop here, and I'll call upon Professor Rukmini De from ICTS to give a small introduction to the speaker. Thank you very much.
Hello and welcome everyone. I'm Rukmini, mathematics faculty at ICTS. It's my great pleasure to introduce Professor Urbasi Sinha from Raman Research Institute today. She is leading the Quantum Information and Computing Lab at RRI. This lab specifies in experiments on quantum information processing, including quantum computing and quantum communication, using single and entangled photons. So we will hear more about that. Urbasi did her PhD in University of Cambridge in the UK, and she did a postdoc in Cavendish Lab in Canada, again in Cambridge, and IQC in Waterloo. And as you can see, she is still a associate faculty of IQC. And she is also an associate faculty of QuIC, University of Toronto in Canada. One of her noted pieces of work is a novel experimental test of the Born rule for probabilities in quantum mechanics. She has received the Homi Bhabha Fellowship in 2019, which recognized her research and outreach activities. And recently, she is the recipient of 2018 ICTP ICO Galileano Denardo Award in Optics. So with these words, I would like to invite Professor Urbasi Sinha. Before that, I would like to ask Rajesh to hand over a memento to her.
So I'll switch it on from, oh, it's already switched on, okay. So, good afternoon, everyone, and thank you very much for inviting me to the Kaapi with Kuriosity lecture. It's, I mean, you know, you're used to giving technical talks, but then it's so much nicer to talk to a group of people who are perhaps more curious than the audience in a technical talk. So then I'm really looking forward to this. And thank you, Rukmini, for the introduction. Of course, I will get an award next year as well. It looks to me. The Homi Bhava, I got it last year, but 2019 she has declared. So I'm very pleased with that. And of course, thanks to ICTS and the Jawaharlal Nehru Planetarium for this forum, the Kaapi with Curiosity, which I have watched on YouTube so far, actually. But then now I'm here, so thank you. So the title of the talk is Fascinating World of, so just one second, this works, right? Yeah. Fascinating World of Photons, Superposition and Entanglement, and of course you are aware of the affiliations. This is the Raman Research Institute, and of course, you know, this is a local institute. So this is the advantage that if you really have questions which are too deep to be answered today, you can come over to the lab. Because it's almost next door, considering it's in Bangalore. So please feel free to come and visit us and talk to us more. This is a statue in front of the lab, a pose that many of our students like to take sometimes. Today we have a live demo. We will begin with that. Right? So hopefully it'll work and so on. Of course, we have a quantum optics lab, as was mentioned. It's a class 10,000 clean room. Now, what is a clean room? Well, it is a clean room. It's a room which is clean. But then, of course, it's more than that. It's got less than 10,000 dust particles per cubic foot. And here we perhaps have 10 lakh. So we have a couple of orders of magnitude improvement in our lab. And that is essential because we work with you know, a lot of interference experiments. And if there is dust, which is too much, sometimes you see Newton's rings because of this dust particle. So just to avoid that, you need a modulated environment with precise control on temperature and humidity, as well as dust. So that's what we have. And we work on these areas of quantum information, computation, and communication, as was mentioned. This is how the lab looks on a good day when students are outside, and this is getting photographed, right? So this is an air shower and an air curtain entry. So, you know, if you walk in, you have to wear clean shoes and so on, but if you have some loose dust particles on you, there's going to be this big blow of air which is going to come on top of you and get rid of those. So that is the idea behind this. So soon you enter the class 1. This is class 100. Which is much better than 10,000 in this case. And then you enter the 10,000 area. So that's how it works. And so, of course, an optics lab usually looks like this with an optical table and several components. And we have a little demo here of a small table with some components for you today. So these are the areas, as was mentioned. And of course, these are the, you know, more important ingredients, so to speak, because without them, the experiments really wouldn't work. So we have 8 PhD students now and other students in different capacities. Surya and Shwanchari are here today in the audience, and they're going to help with this demo and make it work. And so we are very thankful that we have so many interested people working with us in PhD as well as in other temporary positions and enriching our research that way. So with that, I will go on to why we are actually interested in all these problems. Well, the big picture is actually it's a little bit of a downer. So the understanding that we have, the theoretical understanding of the universe that we have is rather incomplete, right? So now you know that, we have all this dark matter and dark energy, which forms around 80% is what I was aware of, but some astronomers told me that it could be even more than 90%. So it really is a lot we don't understand, so which is not so great. So then what do we have to do? So we have to hold on to things that we do understand, and then how well do we understand the laws becomes very important. So of course we're talking about laws of physics should be able to describe most things. So these laws of physics that we hold sacred, how precise are they? And so what we do, one of the important things we do is fundamental tests of laws of quantum mechanics. So we do precision tests, like for instance, it was discussed in the beginning that we had done a test for the Born rule, which is usually the second postulate in quantum mechanics textbooks. So indeed, how well do we understand it, up to what precision? So that becomes an important thing to understand, considering we don't understand a lot. So what we understand, we need to understand up to a certain level. So this is sort of one of the areas we're working on. Then, of course, comes quantum computation, which I'm sure many of you have already heard of in different fora. So this is a very important research direction, of course, and quantum computers are projected to be able to solve certain problems for which there is no efficient classical algorithm. Now, note the word it's projected to be, because at the moment, we really don't have, at least the algorithms people, the theory, computational complexity people, they don't really have an algorithm which will work for a problem which the classical computer just cannot solve. So this is not the most important thing we are looking forward to, but this is important, that some solutions will be exponentially faster than what is possible in classical computation. So a quantum computer is not just going to replace this laptop tomorrow. So, you know, we are very excited about all the progress that has happened, but we have to take it with a grain of salt, that it's not going to be a magic device which is going to just replace this tomorrow and solve everything faster. No. We are actually developing now quantum processors which are dedicated to specific tasks. And there are certain lists of tasks for which we have efficient quantum algorithms, which will definitely have this exponential speed up. That is where we are right now. Of course, we don't know what happens tomorrow. So that is, of course, the beauty of quantum mechanics itself, that it's probabilistic. But then at the moment, that's the situation. Quantum cryptography, of course, is an area which is much more practically oriented even now, in the sense that we have devices which are sold commercially, which can do quantum key distribution, demonstrate it to you, and so on. So it's a more, it's somewhat a more advanced application than quantum computing is right now. And it is supposed to guarantee, quote unquote, perfectly secure communication. So our lab actually deals with experimental as well as theoretical problems relating to these areas, fundamental tests, quantum computing, as well as quantum communication. So this forms the basis. And so as was mentioned, so what we are working on, of course, there are different ways in which you can do quantum computing. You can build up devices which have different physical manifestations. We are working with light. Clearly. So we are working with photons. And now what I've said here, that we manufacture different types of single photon sources. Now what does that mean? I mean, if I make this tube light dimmer and dimmer, then of course I go to a regime in which I have fewer and fewer photons constituting this light. But that is different. What we need is a source which is actually a source of true single photons, so to speak. And that is different technologies. It requires nonlinear optics, which is what we have been developing for the last several years in our lab. And then these photons could be entangled. That we will come to shortly, what is entanglement and so on. And so this is our area. We are working with an optical implementation of all these problems that we just discussed. And so this is an example of a photon source in the lab. And this more interesting one, of course, this you would have seen. In fact, it's somewhere there. So then, the photons which come out, they come out in pairs. So they actually populate cones. So we won't get into the details of how that comes out through the mathematics. But then this part here could be one, and its pair could be in the other cone. And these cones, they define different polarization states of light. I will talk about polarization at some point, but I'm still sure that many of you already know what is polarization. So now this particular point here, is an interesting point, because it could belong to either cone. And so we don't really know a priori which one it belongs to. So that is what defines this Bell state, which you have heard of. It's the state in which if the first photon is H, then the second is V, and the first is V, second is H. So here we have that Bell state defined. And so if you want to work with entanglement, you have to work with photons coming from here or here, depending on the setup, right? Okay. So now, of course, that was the bigger overview of, what we are doing and to some sense how we are doing it. But then, of course, I go back to 1965 now. And who is this, by the way? And the problem is I can't ask a question. I've already answered it if you're observant. But then this, of course, is a very, very famous Nobel laureate in physics, Richard Feynman, who famously said that I think I can safely say that nobody understands quantum mechanics. And this was in 1965. And of course, 2018, so we are 53 years down the line, we'll add a little, mark here and say nobody completely understands quantum mechanics. Because of course, 53 years, we have understood a little more than maybe in 1965. But what is the beauty is that there is still so much more left to understand and explore and apply, which is what makes this somewhat a timeless statement. Because still new phenomena will keep emerging, and that's the beauty of this subject, right? So, and of course, there are examples of several devices which hopefully these are the ones you're more familiar with and not so much this one. But then the idea is that you know that all these applications that you see, whether it is, just, the laser or, the CD or even the MRI machine, all of them are based on laws of quantum mechanics and so on. So quantum mechanics is a theory which has found already several applications. And then we talk about more, which we talk about in this talk, right? Okay, so now I go on to actually discussing light itself, because I want to start focusing on the photon aspect and how I'm going to use the photons in the rest of the talk. So light, of course, is very interesting because, so we have Max Planck here, who found that light can behave as a particle. I mean, you're aware of this. He got the Nobel Prize in 1918 for this. Albert Einstein, of course, actually discovered what is the photon, the packet of energy, and he explained it through the photoelectric effect, which you have studied. And so he got the Nobel Prize in 1921. Then we have the matter. So essentially, both light and matter can have a particle and wave behavior. That's what I'm coming to. The first thing I want to discuss is the wave-particle duality. Okay? So here we have the Bohr model of the atom, which is about matter. Niels Bohr, Nobel Prize, 1922. And here is Louis de Broglie, who actually came up with the de Broglie hypothesis, where he says that the wavelength associated with matter is inversely proportional to its momentum. Right? And momentum is mass times velocity, as you're aware. So now this is an interesting, it's a very important equation for me, because it helps us in understanding a little bit as to what perhaps is quantum. This is still a question. So when do we call something quantum? When do we start needing the quantum explanation for things? And when is it not necessary? So now, for instance, if I give you an example, now this I won't demonstrate, but suppose I go and hit myself against the wall, right? Now, what would happen? Yeah, but you should say I will get hurt. So that is the first thing which will happen. But then, of course, what won't happen is perhaps I won't tunnel through the wall, right? So then, because, I am a massive object, not so massive, but then compared to the electron, quite massive, right? So even if so I'll have to really move. How fast I'll have to move can be a homework question. Assume a certain mass, which is kind, and then you will see that this lambda is not really comparable to my size, right? So then this sort of gives us an idea as to, this question that I have as to what is quantum. So when things become smaller and smaller, then of course, these things start mattering, because they actually compare to the size of the particle. So if an electron did that, there is a finite probability it will tunnel. Right? So then that's the idea. So we have to, this is an open problem though. It's actually a philosophical question, that where is the quantum classical divide? And so we don't know the answer to that question, but we do know safely where we can start really worrying about the quantum. Okay? Now I go back to my Nobel Prize series. So we have Thomson and Davison, who won it in 1937, as you know, for this Davison-German experiment. You're aware of that, George Thomson. And double-slit, yeah. So now comes the favorite experiment, one of my favorite experiments, which is the double-slit experiment. And you know that the double-slit experiment can be performed using light as well as matter waves, and it's the most beautiful demonstration of wave-particle duality. And in fact, New York Times had a poll, I think in 2009 or 10, which experiments people like and so on. It was voted the most beautiful experiment in physics. So indeed, there is a lot to it, and in fact, Richard Feynman, again, said that it contains with it all the mysteries of quantum mechanics. So we will also demonstrate a version of that. So indeed, we can explain a lot by just the double slit, and still understand not everything. So that is the things. Okay, now modern quantum mechanics pioneered by Schrodinger, Dirac, Heisenberg, and Max Born, and they all won Nobel Prizes in a sequence in several years. So this is actually something, there is a point here to be made. Quantum mechanics is a very, very rich theory. And many, many seminal contributions have happened to it over the last century. That is why, people have been awarded with the highest prize in science so many times. It's not a fluke or anything. It's actually true that so many contributions have been made, and still more are waiting to happen. Right? So this is actually a very beautiful realization that you make after this. Okay, I come back to the question as to what is quantum mechanics, and this is the Young's double-slit experiment. So I think I have a video, and hopefully the first one works, then most of them will. Okay, so it is working. So now what I've done here is, this is of course a simulation experiment. The real one will come towards the end of the talk. I have a slit here, or an aperture, yeah. So I'm making it smaller and smaller. I'm decreasing it. And then what I'm doing is, of course, I'm going to incident light on it. And I'm going to do the same thing, and I'm going to show you what happens. So we're going to try this with very small slits. So then as the slit size becomes smaller and smaller, what happens is that instead of a point, it spreads out like that, and we have bright and dark fringes. So bright and dark fringes, of course, as you are aware, is a wave characteristic. So then we can understand this behavior of light by saying that light actually behaves like a wave, right? So what is a wave now? Just to remind ourselves, we have, the water wave is the most common example. So you have a tank, and you have these two objects here which are moving up and down, causing these ripples to form. And so when these ripples are forming as they are going forward, you can see that, they merge together and form an interference. So light also actually is showing something similar. So I'll just replace this with a double slit scenario. So instead of the water, now I have the slit as a source, and then I have light incident on it, and this is the kind of pattern you would end up getting in a double slit interference. So light is a wave, right? Or is it? Because it's a question. What if we see, no, don't worry about the slowing down. It's more about actually reducing the intensity down to a level that we have only one photon passing through the slits at a time. Okay? It's not that the velocity has decreased or anything. That's not what we mean. And so then what is happening here, courtesy Alain Aspect, is that, again, the same thing is happening. Even though one photon is going through the slits at a time, we are building up an interference pattern over time, right? And so this is the question, of course, and how can light arrive one by one and still show interference? So this is the demonstration of the wave-particle duality, that every single particle behaves as a wave. And this is an interesting take on it. You can read this word both as a particle and a wave. So, this is, okay, this is turning out to a live demonstration of wave-particle duality, but this is actually the first concept I wanted to establish, very important actually for the experiment we will show. Okay, and this is the, it's from the web, the interference pattern which is formed by single photon build-up and so on. Okay, now we go on to the second concept, which of course is superposition. Now, superposition, I think again, you're aware of when you talk about it in the wave scenario. So you have these two waves, and when you add them together, you get this. And then when you have them out of phase or in phase, accordingly you get constructive or destructive interference. So here you get nothing, and whereas when they are in phase, then you get the bigger amplitude. So this is what is the superposition when it's applied to the waves. Now, of course, I'm going to go on to discussing what is superposition in a quantum system. What happens in a quantum system? And this, of course, is very interesting. So you have the concept of a quantum bit, which we are now going to explain. So now of course, this audience here consists of mostly an average age of 19 or something like that. So you are much better at computers than us. People in the front row are probably much worse at it. So I think the computer savviness is increasing. It's inversely proportional to age these days. So you're very well aware of how this computer works. So you have transistors. And what does a transistor have? It can have the off state and the on state. And so then that can be represented by the 0 and the 1. So this is what is a classical binary digit or a classical bit, right? So it can be in the off state or in the on state, okay? Now, of course, comes this interesting question that if I were to tell you that can you actually come up with a scenario in which the transistor is a little bit in the on state and a little bit in the off state? So it's very difficult intuitively to think about it with a classical perspective of such a scenario. It's like, the switch is somewhat, we've arranged it in a way that it is neither on or off. That doesn't happen, right? So then that's where this thing, our classical intuition kind of breaks down. And the quantum bit intuition has to take over. What happens in that is precisely this, that of course you have the 0 and the 1 again. It's a two-level system. Qubit is a two-level system represented by the 0 and the 1 again, let's say. But what we can then discuss is this concept of a Bloch sphere. But then in other words, any point on this sphere is a part of 0 and part of 1, right? So this is the North Pole and the South Pole. And any other point is going to be partly 0 and partly 1. So it's alpha 0 plus beta 1, where alpha and beta are complex probability amplitudes. And so then, of course, they have to satisfy the normalization condition that I'm sure you're aware, that mod alpha square plus mod beta square is 1. That has to be there. But other than that, they actually have a lot of freedom given to them. And in fact, a qubit might seem to contain an infinite amount of information because the coordinates can encode an infinite sequence of digits. But one has to be careful here. Indeed, we have this, but then when we measure, we again collapse to either the 0 or the 1. So that, the probability of that is governed by alpha and beta. And this alpha and beta can take up, can sort of collaborate and take up many pairs of values, satisfying that condition. So that is where the concept of a qubit comes in. This is what is called a superposition state. Partly 0, partly 1. Again, classically, it's very difficult. So we'll come to another interesting example, which some of you would have seen in sitcoms and so on of superposition state shortly. So now, you know, so just, you know, you have 1 bit, 1 qubit, 2 bit. So let us just consider the 3 option. So I have actually 3 classical bits. And if I have that, these are the possible values that this can take, right? So it can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 1. So there are 8 possible such values. So this is what it is. So it's 2 cubed 8. So now what we have in the quantum bit is the possibility of superposition. So this is where, you know, we have actually access to an 8-dimensional state space. Whereas here it is one or the other or the other or the other. So that is where the difference comes in. And so now if I actually go on to 50 qubits, then I have this number here. Now this is a question I haven't answered on the slide. So what is P? Okay, so yeah. So the answers are not loud enough, or people are not confident enough, but then it's, I will pardon you for that, because we don't really study this in our number system. So people like us, we go up to 1,000, lakh and all, then people there go up to million, billion, and so on, but trillion, but then after that, of course, comes billion. So billion is a number we don't usually encounter in our daily lives, and so this is actually supposed to be a huge number, which we cannot imagine. And so this is the kind of state space that we would have access to. So this is the general idea. And there are lots of devices which are proposing to be possible qubits, you know, and some of them are, of course, photon-based and so on. And I will not go through the details of where they are and so on that I can discuss. And this is Sergei Haroche and David Wineland, who won the Nobel Prize in Physics in, I think, 2013 or 14, for their contributions to ions, single ion and single photon experiments towards quantum information. So the, you know, it's not that it stopped in the even now we have people making seminal contributions, right? So, so that is my little discussion on superposition, which of course is going to be very important again for most of the talk. And now I go on to another concept, which is of course entanglement, right? Now entanglement is a concept, you know, what I will do here, you know, for the sake of our time, as well as, you know, the fact that we want to do the experiment. So many things we have to look forward to. You don't know, actually. It's a long talk. So I will not go into the mathematical details of the subject because, you know, or exactly how things work, because that is tricky. Then you should come to the lab to see the entangled photon source and so on. Now what I'll do is actually give you a little bit of a picture for what happens in entanglement, but don't think it's accurate at the mathematical level. So take it as a demo of the phenomena, okay? So whatever I say next will have that flavor, okay? So this, of course, is Surya actually made this video. So he prefers historic characters. So this is, Chanakya is cut out from this for some reason. So this was supposed to be Chanakya. Huh? It is, no. Somehow it is above. No, I will play it. Yes, thank you very much for that advice, but good. So when you play it, Chanakya comes in. Now the one important point to be noted, which I noted before coming to this lecture, is that they're not from the same time zone. Yeah? So, but then this is also an interesting point about entanglement. Once you produce entanglement, the idea is that it should survive. You know, and so then this is probably the reason behind why we have Chanakya as the producer and Akbar and Birbal, who are clearly not in the same time zone, as the receivers. And so what is Chanakya doing here? He's producing a pair of entangled particles, you know, balls, whatever. Photons is going to be a bit tedious for him to do, given his era. So, right. So that is what is happening here. So he's going to give rise, he's going to produce these two balls here and particles. This is, we don't know what is the color you can make out. Could be red, green, anything. So Akbar is asking him, you know, what are the colors? And he says, no idea. Then he opens his box. This is green, so what are the colors? He asks again. Birbal says, mine must be red. Okay? So turns out to be red, right? So how does Birbal know, of course? So, you know, so that, of course, is because, you know, these were an entangled set of particles. So that is the whole point, that once we have this knowledge about what Alice, let's call it Alice and Bob, because that's more conventional. So once we know what Alice is doing, then, you know, we have an idea of what is happening to Bob. I talked about the photons and the intersection point, and I said, if I know this is H, then the other one is V. But if this turns out to be V, then the other one is H. And so then because we don't know a priori, it forms this state, which is called an entangled state. It's a very famous state, it's a Bell state, and you cannot actually write it as a product of the two subsystems. Okay? So that is, of course, an important point. Now I go on to that example that I promised you a few minutes ago, which is a popular example now, thanks to the Big Bang Theory, where they have actually used it in one of their episodes to explain something. So Schrodinger cat experiment. So what is a Schrodinger cat? Well, of course, Schrodinger actually proposed it clearly. So this is a cat. Now don't, please, there is no animal rights violation here. It is just an example, a demonstration of a phenomenon, right? So this is a cat which is sitting inside a box. And I have, unfortunately, I have cyanide also in the box. And the cat can take that cyanide and, you know, not live anymore. And then it doesn't, then it does survive, right? So what I have actually done is, I haven't done it. Okay, but then what is happening in this thought experiment, so to speak? But the Schrodinger cat state has been produced in the lab and so on. It's not quite, but not with a real cat. Yeah. So then I have also a source of alpha particles, right? A radioactive nucleus. So now what is going to happen is that if this alpha particle remains within the box, then the cyanide does not get consumed by the cat. Okay. As you do it in a way that as soon as the cat consumes the cyanide, alpha particle comes out of the box as an indicator that the cat has had the cyanide. So what I'll have outside the box is some sort of a detector which is going to detect alpha particles. So if I detect this alpha particle, then I will know that the cyanide has been consumed. If I don't detect it, then I'll know it hasn't been. So before I do that experiment, now think about the cat in the box. Because I'm outside, and of course I'm not going to allow myself any undue advantage here. So I'm outside, the cat is inside, and I know the cyanide is also inside. So at a given point in time, the cat could be either dead or alive, or in fact, a little bit dead, a little bit alive. So, I mean, that is the idea of superposition. So the cat being dead and alive at the same time, because we don't know what is happening inside. But as soon as this particle is released, of course, we know. So then, of course, we know whether it is dead or alive. And what does that actually determine? That actually forms what is called an entangled state. So this state of the alpha particle is entangled with the state of the cat, right? So if this alpha particle is within the box, an alive cat is happy. And then if the alpha particle is released, then of course the cat has had the cyanide and it's kind of dead. So then this is a very important concept actually in quantum mechanics, in quantum measurement. What happens in quantum measurement is that you try to measure the quantum state, but then you basically link it with an apparatus state or in some sort of pointer state it's called. Okay? So by observing what is happening to the pointer, you can figure out what is happening to the quantum state. So this alpha particle is like a pointer. So measurement is an entangling operation. So that is the idea. So this Schrodinger cat is a very illustrative example because it illustrates both superposition and entanglement, which I've been talking about so far. And of course, this is the whole picture. Right. Now I go on to another example of entanglement. And again, the caveat is don't think of it in mathematical terms. But think of it, just for what it's supposed to be, to give you a feel for this thing, which is very difficult to feel, by the way, because it's a correlation which is stronger than classical and, in fact, rather non-intuitive. So now I'm going to tell you that this is an orchestra, okay, which you can figure out. And let's say it's playing some beautiful piece of music by Mozart. So this orchestra is happening. I'm in the front. I'm lost in this beautiful music. Suddenly, I come up with this mad idea that I say, no, I don't want to listen to the whole orchestra. I want to listen to the individuals, what they are playing. So I say, okay, the pianist is the only one I want to listen to. Everybody else, please stop playing. So I listen to the pianist. It appears quite random what he's playing. It's not quite related to what I was hearing earlier. Then I say, no, pianist, you stop. Maybe the violin player is going to help me somehow. Again, it's fine, he's playing. Of course, these are all good players. They are working in synchronization. But I don't really make out this connection with what I was hearing in the beginning. So when I actually listen to these individual pieces of instrument, I just can't listen to them and then construct what I was hearing in the beginning. So I have to listen to them in totality. So this is called holism in some sense. And so this is what is this very famous description of entanglement. Whole is more than the sum of parts. So just the sum is not going to help. You have to listen to it fully. Only then that beautiful thing will emerge. So this is what actually happens in entanglement, but this is just an illustrative example of not the actual quantum physics. So this is a little bit about entanglement. Right? Now I want to just remind you of polarization, because this has nothing to do with what I've been saying so far. It's a concept that this I'm sure you are aware of. And so I just want to remind you, because it will be very useful for the experiment. Okay? So I have this, light is an electromagnetic wave, as you're aware. So it's also a transverse electromagnetic wave. So the direction of propagation of light, there is one, let's say. And then the electric field is actually vibrating perpendicular to that. Right? And so it could, any of these would define that perpendicular direction. Right? So if I have no such constraint, it could be any of this. So this is an example of what we would call unpolarized light, because all of this would sum up to no definite direction. All are possible. But now this goes through, and this is what is called a wire grid polarizer, which I have shown here. A polarizer is a device which actually selects a certain component of polarization. So here I have ensured that it is a polarizer which is actually only allowing, let's say, this particular component to go through. And the rest gets absorbed by the material and so on. And we have things like that in the demo. So what happens is, then from this I can extract, let's say, the horizontal polarization, the vertical polarization, and you can realize that one will be this way, the other will be this way. So if I combine them, I won't get interference. So horizontally and vertically polarized beams will not show constructive interference. So this is just something that you should remember for 10 minutes down the line. That's why I just wanted to give you a little reminder. So just to little pause, this is the first part of the talk. And so what we have discussed is the general idea of superposition, the even more general idea of entanglement, and then of course a little bit about polarization for the benefit of the experiment. Now what I wanted to spend a few minutes on is why I am giving this talk. Of course that introduction helped, but then still, put it a bit in perspective of the experiments we are doing. And, it so happens that they are related to exactly these concepts of superposition, entanglement, polarization, and so on and so forth. So that is going to be discussed in the next few minutes. One of the things I wanted to talk about a little bit, but, again, in a more general fashion, is this work we had done, in which we actually showed that the superposition principle, which we have been discussing so far, is usually incorrectly applied in interference experiments. Okay? And what we, along with collaborators, what we showed is that there is a correction term to this principle in interference experiments, which can actually be quantified and then finally also measured by us in an experiment. So this is directly related to why I talked about superposition for so long. So then I will use a concept called Feynman path integral formalism. But then, you don't need to know anything about path integral formalism to appreciate the contents of this, okay? So this is just an alternative way. So you heard about the Schrodinger equation and all that. I think you are familiar with. So that is, if you solve the Schrodinger equation, you get the solution to the equation's wave function and so on. The path integral is an alternative approach to get the probability of going from a source to a detector. So that also gives you the probability. And so we'll keep to that, actually. So again, a reminder through our favorite so far, superposition principle. So this is just to tell you that there's a connection with what you have been seeing so far. You remember this, destructive interference, constructive interference, and so on. And then I will go on to this argument that if I actually have boundary conditions which are different from each other, then does the superposition principle hold? Okay? Of course, the point is that and in fact, we could look at it from a Hamiltonian perspective. So I've given you a picture here. So this is a single slit, okay? Let's call it A. And I have some source incident on it, of some electromagnetic waves or anything, electrons, photons, some source. And then, of course, there is some wave equation which is going to define that, some equation. And this actually is a certain boundary condition that I impose on it. And I get a solution. I call it psi A, okay? Then I have a second slit B, which is, of course, spatially separated from A. I open that. I have this wave function, psi B, okay? The question that we are asking here is that if we opened both the slits together, then is the solution just the sum of psi A plus psi B? And of course, since we are asking the question, the answer had better not be yes, because it's then it doesn't make much sense. And now you should understand why it is not yes, because this is a Hamiltonian, this is a second Hamiltonian, this is a third one. If you look at it from a boundary condition perspective, this is boundary condition 1, 2. You can't add the solutions to 2 different boundary conditions to form a solution to a third one. And that's what we are actually doing here by saying that psi AB equal to psi A plus psi B. And we have been saying that. Not we, I mean, community, several known textbooks, we have been doing that. And then we do that mod of psi A plus psi B whole square, call it interference. So that is not quite correct, right? So this is what we actually went on to investigate. And we did this through these papers here, where we did, this one, these two actually, we did the theory estimate of a quantity which would, sort of quantify this deviation from the correct, from the naive application towards the correct application of superposition principle. And then, of course, we'll discuss path integral, but again, before that happens, let me tell you, so this is again an illustrative example. So I'm going to show you different types of paths which can happen in path integral and tell you which are the paths which will contribute to this non-zero term. But bear in mind, these are Feynman paths, and they are supposed to be probability amplitudes. They may not be the real path the particle is actually taking. So don't think the ball is going forward, backward. It need not be like that. So that is where we'll keep it. So these are probability amplitudes, and these are discussed in terms of paths, okay? So now we have this source, and it's supposed to be emitting these red photons, and this is one way in which it will go through the slit. Okay. This is another way. So it goes through, hugs the slit plane, and then goes to the detector. We call them hugging paths. And then another thing to do would be to go through one, and then the other, and then come back through the third one. So this is also something which has a weight, a finite positive weight in path integral. So what path integral tells you is that all paths are possible. Of course, not all paths have the same weight factor associated with them. So the first class that I showed would be the classically dominant paths. And they would clearly be dominant here as well. But the second and the third type, which I showed you, which are not going to be classically dominant, are what we call non-classical paths in the paper. And they would lead to this correction term. Now think about it. If I had only the single slit open, then these classically dominant paths would happen. But if I had two open, only then the probability for these second and third type will emerge. So then this is the additional factor which comes in terms of the path integral language, which is what we quantified through this quantity, which we call, which is called the Sorkin parameter. I will show you what that is shortly, and showed that it is indeed non-zero. Okay. So Kappa, we call it Kappa. This is actually, there is actually an anecdote behind this Kappa. Sorkin parameter, in his paper, he calls it IABC. So it's the second order interference term, which happens in a triple slit experiment. We call it Kappa. That is because, we actually have added the contribution which will happen when no slits are open. So we want to actually always motivate some experiment, right? So in the usual case, the situations would be all slits open, 2 open, 1 open. But no slits are open, you don't expect to detect anything, but you still do. Because in an experimental scenario, a detector will have dark counts. So we add this 8th term there, we will see that. And then that becomes an experimentally measurable quantity. And this is very interesting, that experimentally measurable quantities tend to be Greek symbols for some reason. You must have noticed this. So then as soon as it became experimentally measurable, it became Kappa. Okay? So this is the history behind Kappa. And so of course, lots of experiments and theory have actually happened on various aspects of this problem, which we are not getting into now. And so this is Raphael Sorkin, who actually proposed this quantity. So I'll go straight to the quantity. So if you have a single slit, then of course the particles are just going through. So the probability is just, there is nothing very non-trivial which happens here. This is a trivial situation. When you have two slits open, then of course we know what happens because we have the interference. So when both open minus the sum of the singles actually gives you the interference term, right? Now this is called first order interference, and it agrees with quantum mechanics. Now if I want to go to second order interference, which is the 3-slit term, then of course I can similarly define this quantity, which is all 3 open minus the sum of the doubles plus the singles, okay? So this is the algebra, but then just to note, we talked about Born rule, the second postulate in a textbook, that is probability is mod psi squared, right? And then of course here we have this assumption that the psi is psi A plus psi B plus psi C. So then of course, if I were able to, so now if I make that assumption go through the algebra, this particular term, IABC, as I said, becomes 0. okay? But now I'm questioning this, right? I'm saying that this is actually not true. Psi is not psi A plus psi B plus psi C. So if I were to do an experiment or theory which actually focuses on this IABC and we find it to be a non-zero, then I actually prove what I'm saying is correct, that indeed it was never meant to be zero anyway. So this is what we have gone on to do in the theory as well as experimental works. And this was the first experiment that I had done when I was actually still a postdoc at IQC in Canada. And so this was the first triple-slit experiment, which of course gave us a very nice zero. And that is what has been happening for the last 10 years, till our experiment, which we will show you now. Okay, so yeah, I'm just very happy that it's non-zero, so it's blowing up like that for some reason. And so this is actually very important, that in this work, we actually found a formula for this quantity. So an analytic formula in terms of length scale dependent parameters. Now this is something which you will appreciate. If you're a theoretically oriented person, you would like a formula, period. But if you're an experimentally oriented person, you like it even more, because then you can use it to design an experiment where you can actually make this large or small. So this lambda is the wavelength, D is the interslit distance, and W is the slit width, okay? And so under certain assumptions, this formula holds. So it gives you a clue of how to design an experiment to make this non-zero, like crank it up somehow using length scale to your advantage. Okay, and then of course the other thing which we are very proud of is that, you know, this blue line is our formula. The black dots come from some very complicated simulations called finite difference time domain simulations of Maxwell's equation. Won't discuss that here. But then the point is that simulation took those authors 3.5 days of computation time on a supercomputer and 6.3 terabytes of memory. Again, you know what this means. And our formula worked on this particular computer almost immediately. So this is a very important message that I usually like to share, that, you know, sometimes simplicity is beautiful. Of course, you can do the complicated math, but then sometimes you can have a simple formula which agrees very well, and that gives you a feel for it. Then you can use that and design your experiment, and don't have to worry about the complicated ones all the time, right? Of course, this is what I'm heading up to. Apologies to the front bench. You know, the point is that this is what we do, you know. We really like to work on theory which is experimentally verifiable to the extent that we are capable, or we leave it to other experimentalists. So this is the idea behind even this theory work that I talked about. Yeah. Yeah. So of course, you know, the first, so a little chronology of these experiments. The first experiment, as I mentioned, was done to test Bond rule. I told you that, you know, there are two assumptions. One is psi A plus psi B plus psi C itself, and the other is the square law. So the square law also can be tested with these experiments. But then that was with the assumption that this quantity is going to be zero otherwise. But now we have challenged that. We have said it was never meant to be zero. So that is actually the first level that you need to cross, that, you know, understand it at the non-zero level, then go on to any Bond rule test, you know. So that is why our work becomes kind of important here. So this is using single photons. Skip how photon sources are made, but then, you know, this is what I said, it's a nonlinear process, this is a nonlinear crystal, and so on. And this is how it looks on a neat day. And this is just to guide the eye. So this is a pump laser, which is a strong laser, and it leads to a down conversion process, which means one photon splits into two. So the two actually add up in energy to the first one, and so on, and energy momentum conservation has to be done. And that is what takes a lot of time and effort, of course, in alignment. And so, and this is, you know, how it looks. This is the entangled state we had mentioned, the experiment. And so what we went on to find is that this was bounded up to 10 to the minus 2, this quantity. So now, I'll ask you a question which I'm sure nobody has asked you before. What is zero? Something that Indians may have discovered. But that's not the point. The point is that in an experiment, what is zero is very crucial. Because we never measure this beautiful number zero. We always measure it to be non-zero. But then we have errors. Everything comes with some limitations, right? Your experiment will always have some limitations. Instruments will have their limitations. That will add up to a certain expectation. So if your result is lower than that expectation, then it's zero. Because of course you don't have a control on it, errors are higher. If it is higher than your expectation, then you can claim a non-zero. That is why with all these experiments, you know, this is a grating-based experiment that was done, which was a bound of 10 to the minus 4. Then we had an NMR experiment done by a group, again 10 to the minus 3. So far, you know, and there are others, everybody has measured a 0 because the limitations of the experiment supersede the quantity that we are actually trying to measure. This particular group in Rochester and Ottawa actually has done an experiment where they claim that they have found the signature for our, these non-classical paths by measuring a non-zero Sorkin parameter. Okay? So they have done a single photon experiment, and what they have done is they have used a gold film and etched slits in it, okay? And then done the 3, 2, 1, as I mentioned. But this gold usage is what they highlight, that gold actually leads to the production of what is called surface plasmons. And these surface plasmons leads to some kind of enhancement at the boundary, which leads to a higher value of this quantity kappa. So this is a material-induced enhancement, not quite the geometry effect that we were looking for in the Sorkin parameter. And this is one of their experimental graphs. So these points here, these circles, those are the experimental kappa values as a function of detector position. These are the attendant error bars, you can make out. Yeah? And this is the theory prediction. Okay? Everything seems to be blue for some reason, but this blue line is the theory. These blue circles are experimental points, and the blue lines which are surrounding the experimental points are the error bar. What strikes you immediately when you see this graph is that they only measure negative values. They actually don't have any measurement here in the positive, nor do they have any measurement in the slope regions. So essentially, the experiment is precise up to a level that they can only measure certain values. So we, of course, have to do better than that, because otherwise, to claim that this is matching this is a little, little bit of a push, right? So we have to do something better. And so what we do better is actually go on to a video which is too big to include within the presentation. So this is our experiment, which we have done to measure a non-zero value of the Sorkin parameter. We have actually done this experiment on an open field, 100 kilometers from RRI, in an observatory called the Gauri-Bidnor Observatory. This is a horn antenna. It's a source of electromagnetic waves, okay? I mean, of course, that's what you need. You need a source, you need a boundary, and you need a detector. These three things that you see here, these three, I think we'll zoom in on that, perhaps. The camera is shaking, So then, these are the three slots, okay? And they are supposed to be perfect absorbers for these microwaves. We can discuss later why slots, not slits. And so these are the three slots. This is a close-up of our beautiful slots. Then comes this antenna here again. This is the receiver antenna, and it is put on a rail. So the idea is it's going to move along and measure the interference pattern. So this is a very macroscopic experiment, as you can make out. And of course, this is a cornfield, and so on. I'll tell you about the cornfield, but I'll just see, this is how we do this. So these are the two slot case, and my student Rengaraj, who's the lead author in this. This is a single slot case. So what you see here is a simulation of how the wave propagation changes. And now you see the results. And this is not the result. This is actually a simulation of what would happen if these contributions were not there. We would get kappa to be 0. And so this is in fact, you can make out that this is just a fluctuation line, 10 to the minus 15. A very, very, this is our best 0 from Mathematica. So that's the idea. So this is what you would get. But if you actually included this contribution from non-classical paths, this blue band is your theory expectation. These red circles are my measured kappa values as a function of detector's angular position. And these are the resultant error bars. So you can see that kappa is a nicely modulating function. It has both positive and negative values. And of course, it matches quite well with the experiment, given the conditions of the experiment, which of course is not how precision experiments usually happen on an open field. And of course, yeah. So this is done with 6 gigahertz microwaves, 5 centimeter slots, 10 centimeter interslot distance. And we are doing this experiment at 1.25 meter from the slot plane. Then we have also done it at different distances, 2 meter, 3 meter. As you go further, your signal drops. So signal to noise also becomes worse. So your errors kind of go up a little. Then what we went on to do is do a tunability experiment. So what we are doing here is, we are putting perpendicular slots to the slot plane such that, you remember the hugging paths from the video, so that the probability of those paths actually starts going down when you, put in blockers, so to speak. We call them baffles in the experiment. And what you then expect is, as the baffle size goes up, this quantity will drop. because you have less contribution to them. As you go further from the plane, you have more and more loops, and we have shown that analytically, that the contribution drops when you don't have hugging or nearly hugging parts. So you remove that contribution. So you have a tunability parameter in your baffle size, and the baffle size goes up, kappa will drop. So other experiments cannot do this, because you can only measure, and that's it, and say, okay, it's non-zero. But now I can make it 0, and then make it non-zero again by playing with a perpendicular blocker. So this is called the baffle experiment, which actually makes this even more interesting, because, so you can see how this is actually pretty heavy. And we took a lot of time to design it so that the thermocol stand would actually remain mechanically stable. And so this is the kappa as a function of baffle size. So this is 1 centimeter, this is 2 centimeters. So basically when you go up to a certain level, beyond that, it just becomes 0. So then you can, and then when you remove the baffle, you can again go back to your usual situation. So we have a tunability experiment as well. So, right. So we have shown the video. And so if you want a reference, yeah. Yes, yes. Non-zero kappa is arising because of that, yes. Yes. So then by this, you can actually effectively cancel those contributions and so get it to be 0. And then remove it, it comes back again. Right? So that's the beauty of this. And so you can have a look at that if you're interested. And this is very interesting, a little anecdote for a minute. This also has implications on precision cosmology. How's that? So RRI, of course, is an astronomer's delight. So then we have these groups which work on early universe experiments, right? So they try to detect these signals from the epoch of reionization and recombination and make predictions about what happened in the universe. So even when I say it, it's really, really a long time ago. So the signals are weak. So what do? They have these dipole antennas, which they place side by side, and then they form an interferometric setup to try and increase the signal strength, so to speak. And there, sometimes this assumption goes in, that if you have antennas side by side, you can just add the contributions. You don't need to worry about what happens when they're all there in terms of a kappa-like contribution. But we took in the parameters from their paper and simulated kappa, and you can see that it's a nicely modulating function again, clearly non-zero, again of the order of 10 to the minus 2 actually, what we have already measured. So if they want to do precision cosmology and all these things that people are talking about, then they need to start worrying about these contributions, which will be subdominant but non-zero. And in fact, we have been talking to them, thinking that maybe we can have better error models for them through this. So it's a very different application from what we have been discussing so far. Now, in the next 5 minutes, I will discuss something in quantum computation, which we are also working on. And here, of course, we are working on, so I'll tell you why we are working on it and go on to what we have. So this is about producing correlated Q-trits. Now, qubit we have discussed for quite a bit. Now comes the question of a Q-trit. What is a Q-trit? So in a qubit, you have a 2-dimensional system. So then this state space is 2 to the n. We discussed that. So now what we are trying to do is reach a certain number for n as a community, which happens to be 50. So people think that if we reach 50, then these problems which we think we can solve, we will actually solve them, okay? Now this is obviously proving to be somewhat challenging because we're not there yet. Different lab environments have things like 14, 15 as the numbers they have reached. So there are, of course, problems with this. And of course, I like to give a little analogy that, more and more number of people in the room, beyond a point, they don't like being in it because they get uncomfortable. So this is like a coherent superposition, which is difficult to achieve with more particles. And so we want 50, and it becomes tough. So what can I do? I mean, of course, I can still drive to that 50, which everybody is doing, of course. But what a certain section of the community is doing is actually trying to change the base itself. From 2, if I make it 3, then the 50 drops. So by using a smaller number of systems, I can actually have access to a similar dimension of space. So 3 square is 9, 2 cubed is 8. So 3 qubits and 2 Q-trits have a similar sort of number coming up. So that is the idea. Can you increase the base and drop the number of systems? So this is an example of what is called a Q-quad. Here I have a 4-level system. So now I can give an example of what is very popular here, which is a match of cricket, let's say. And so I say that we have 4 possible, yeah, please. No, the color is just a demonstration that these are different levels. Yes. I can use 1 or 2, correct. So that's the idea, yeah. So then I can pack in more information here, right? So if I have a cricket match and there is a win or a loss or a tie or a rain abandoned or something, 4 possibilities, by using a Q quad, I can declare all these results. But with a qubit, I can only declare the 2 of them. So I need 2 qubits. So that's the idea, that I pack in more information by increasing the dimensionality of the system itself, right? So this is the point, and so qtrit is of course a 3-level system. Qtrit itself is challenging, so you'll have something called a hyper sphere. So then you will have, I mean, I can't draw it, but then your imagination has to kick in, yeah. So, right. And of course, you know, the other thing we would like to do in this sort of an endeavor is produce entangled systems. Again, of course, entanglement we have discussed. Are you putting up your hand or? No, you, okay, fine, yeah. So then, so we have, these are the 2 aims that we have. And we have already, you know, made a single qtrit system earlier. I will skip the demo, we can discuss it later. The idea is that we have already demonstrated a single qtrit earlier in 2012, whereby we played a quantum game. So maybe you have heard of quantum games. Quantum games are games in which we see the quantum advantage. Only in quantum systems you win, and classical systems you are, you know, limited to a certain win percentage. So this is a Aharon-Weidman game, which I won't discuss, but you can only play it with a 3-level system. Okay? So we actually, by playing, we mean we perform the measurements corresponding to the game in the lab, and then we found that we win 87% of the time with single photons, whereas the classical limit is of course 50. Ideally this will be 100, but as I gave a lot of explanation, experiments come with errors, so then you can never expect 100. So 87 was the closest we could get to this limit. So this was a single qtrit. Now what we have done in our lab at RRI is produced a pair of qtrits, okay? And this pair of qtrits is correlated in the spatial degree of freedom. So why is that? So the idea is that, you know, I will go on to the setup. Yeah, this is a nice one. So the idea is that, you know, as we discussed polarization, so we can have 2 possible polarization degrees of it. It can be HV, it can be plus minus, you know, but then essentially 2 orthogonal states we can describe, right? So that is why it can form a qubit. So a photon polarization is a very common qubit. Now if I want to do qtrit, then I can't use polarization. So I have to think of something else. And what I am doing is using the spatial degree of freedom of the photon. A single photon incident on 3 apertures can go through this, this, or this. Because I don't know a priori what it is going through, it forms, so if this is 0, 1, and 2, I represent those by the ket 0, 1, and 2, then the state that I form is alpha 0 plus beta 1 plus gamma 2. That is, of course, the qtrit. So this is how I will use the spatial degree of freedom to define a higher dimensional system. This is the way we are doing it in the lab. And what we have produced is a pair of qtrits which are perfect, almost perfectly spatially correlated with each other. I'll go on to show you how the setup looks, but it looks tedious, so I won't go through the details of it. But here, you know, we are actually modulating the pump in down conversion and producing these qtrits. It's enough to kind of understand that. But this is interesting. So here it tells you that, you know, these 2 qtrits which I have produced, which are the 2 photons from the down conversion, actually share up 90% spatial correlation. Again, of course, 100 would be ideal, but you won't reach that. Right? And then now what we have produced, which we have not shown here, is that we have shown that not only are they correlated, they actually share a quantum correlation, and that they are actually almost maximally entangled. So now that we have almost maximally entangled qtrits, it opens up the floor for demonstrating different protocols based on higher dimensional systems using these systems in the lab. So this is another area in which we are doing something slightly unconventional in the sense that we are approaching it from a higher dimensional system, and you understood so many things you're doing. And of course, electoral polling system also I'm sure you all have entered. This one is not particularly for us, but then more for the Army and the Navy when they want to have some communication. So the idea is that when I want to communicate, I'm communicating with you right now. Hopefully some information is going through. But this is not a secret. It's being you know, shown on YouTube. So there is no secret in this. We are just discussing. But if I actually want to share my you know, credit card details, that is a strategic communication. I mean, you know, I don't want a third party to know. So that requires security of communication. And so far it has been done using classical cryptography. And you might have heard of this, that you have ABC, you encode it into 0, 1, 2, and then you know that this is 0, 1, 2, so you get back ABC. That's the usual description of how the classical cryptography works. So here, one very important point is the distribution of the key that is being used to encode and decode. And this key distribution needs to be highly secure. Now, the problem, of course, is quantum computers. So this is very interesting. Quantum computer is something we are really looking forward to for the different applications it promises to fulfill. But another thing it will do is actually break what is called the RSA algorithm, which will actually make one particular form of classical key distribution perfectly insecure. So it will run what is called the Shor's algorithm, and so that's it. So everybody knows all the details, and nothing is a secret anymore. That's the problem, of course. So then we need a quantum solution, and that's quantum key distribution. And so that leads to quantum cryptography, and this is what we are kind of working on in the lab. I mean, these sort of claims sort of make you sit up, because already people are saying that they have this and that, several qubits, 1,000 qubits, 50 qubits. So lots of things are happening which makes us sit up and take quantum key distribution even more seriously. And of course, we can do this through free space as well as through fiber. But both have limitations. Fibers have attenuation. And free space, of course, I need line of sight. If I want to communicate, I need to see the two people. So beyond, of course, in a ship-type environment, the horizon comes in the problem. So beyond the point, you can't do that. So one possible, so these are various things which have happened. One possible solution would be that I use a satellite as a trusted node for this key distribution problem. So by using that, I can actually also break distance barriers. So the satellite can move from one station to the other, and in principle, break distance barriers in quantum key distribution. And so China has launched one of these satellites last year, which has given a lot of impetus to this program that it needs to be done, and different countries are working on it. We at RRI also have a project with the Indian Space Research Organization, whereby we plan to demonstrate a secure key distribution between our Canadian counterparts and ourselves. So this is like 13,000 kilometers. Distance is huge. So if we succeed, then we'll be very pleased. And so this is our project on quantum key distribution. And these are the participating institutes in this project. Okay, so that brings me to the end of the talk part of the talk. Now we go on to the doing part of the talk, which is actually the demonstration of a simple experiment. So the idea is, I cannot really demonstrate all that I have said in this forum, so come to the lab. But then, some of these ideas might still be a bit abstract to you. So some of them, at least, being done right here, might make it a little more hands-on, and you can come and play with the experiment after the talk. That was the idea, to actually do it yourself and so on. Of course, have some guidance from the two students and myself, because if you do it a little bit wrong, you will not get it back. But that's part of life. So this is an experiment called the quantum eraser. Okay. So again, a reminder. So if you have a double slit and you have, photons incident on it, you know by now that you have an interference pattern. But now if I actually manage to have a device, or the rather artistic eye, looking at the double slits, then what happens is I lose the interference pattern, right? So essentially I just get two bands corresponding to the two slits. This interference pattern goes away if I look. So these two actually have terms for them. This, of course, is interference. And this looking actually tells me which slit this photon went through. So I have which path information. Okay? So which path information and interference cannot happen together. So if I have interference, then I do not know which path it went through. And if I know which path it went through, then I lose the interference. So these are complementary observables, we call them. And this is an example of what is called Bohr's complementarity principle. So, these two cannot have, they are both there, but then the manifestation is either this or that, not together, right? So this is the first concept we need to remember. And the second is, of course, what we will do, which is this Mach-Zehnder interferometer. So you have a source here. You have what is called a beam splitter. It is going to split the beam into two, because we will do it with a laser beam, so it's actually splitting the beam into two. We have mirrors which reflect them onto another beam splitter, which merges them. And then if you do it properly, the alignment actually will take a little bit of time. And once it's done, which we have done before the talk, of course, you will get an interference pattern on a screen. So Mach-Zehnder is like an effective double slit. The same thing, it can go through one slit or the other, so same one path or the other. But this is a handy tool, and it comes in very, very complicated quantum experiments as a basic tool. So this is what we will do. So now I think we will go on to the experiment, right? So the experiment, of course, is the quantum eraser, which I haven't really discussed. Yeah. So thank you, Shonchari and Surya, for putting this up. That is Shonchari. Surya is with the cameraman. Okay. So now we switch to the experiment. Yeah. So I just want to start off this way, that I want to introduce the components to you, because you may not have used them earlier. So Shonchari will start pointing them out. Rajesh, we will switch off the light in the end, because otherwise nothing is visible. We check that. Yeah. So Shonchari, can you please point out the laser, which of course is a diode laser. Hand, is that working? Do you understand? Of course, we are doing this literally live. Your hand is not working, no? Okay, now better. Then maybe this is better. Then lights off. Okay. So Shonchari's finger is pointing at the diode laser, which is, don't touch it too much. Yeah, okay. So that's a 532 nanometer green diode laser and has a power of around 5 milliwatt. Okay. Then she will point you to the first beam splitter. Okay. And so this, maybe we can also trace the path of the beam. Let's call it path A. So the beam is going to go from the laser to that beam splitter, and it's going to split into two. We'll follow path A. It goes on to a mirror, right? Mirror does what it should do. It reflects it back to a second beam splitter, right? Right. So that was path A. So this particular beam went from one side of the beam splitter, followed a path, and went to the second beam splitter, okay? Then the other part of the beam, Shonchari, is on this side, yeah. So that will follow, let's say, path B. And so we have a mirror again there, and then that reflects it off again to the second beam splitter, okay? Now, beam, as we discussed in the talk, the beam splitter, in the first instance, is splitting the beam. In the second instance, it is actually merging the two beams together. And so when it merges the two beams together, what we should have, hopefully by now, after the 1 hour break, we should still have an interference pattern, right? Okay, so this is the first observation. So maybe, yeah, this is visible to the audience, that we, of course, have this, not all the components. So we brought student-grade components. So they're not all ideal. So it's not extremely sharp, but I think you can make out the bright and the dark fringes here. So this is an interference pattern which we have formed in a Mach-Zehnder interferometer. Right? Is there any question, comment? No? You can make it out. That's important. Because, of course, we are literally doing this live. So this is the interference pattern currently behind Shonchari on that screen, right? It's there behind you, right, Shonchari? Yeah, right. Okay. So now what we will do is, of course, so this is interference. This is the first phenomena. Now what we will do is we will put a marker in one of the paths. Let's call it path A. We put a vertical polarizer. One has to remember that the laser beam that we have is actually diagonally polarized. So we put a vertical polarizer in path A. Okay. And so what happens? Again, we have to zoom in on the wall. The interference is there, but actually, because we can't really compare live, you can come and see it. The intensity has dropped a little. And that's natural, because we have only selected a part of the beam and so on. Okay. Now we are going to put in a horizontal polarizer in path B, right? Let's do that. Okay. And now we again zoom in on the wall. And of course, we see the interference has disappeared. Okay, so this is the second observation. So we will go through the observations once, and then we will go through the observations once more with some explanations. That is our plan, so that you see them twice, because you're, of course, absorbing it as I speak. Now we are going to put a third polarizer after the second beam splitter. It's also diagonally polarized. And this required, last time we did this before the talk, a dark room. Let's see if we zoom in on the wall what happens. Surya. Yeah. Maybe we don't need darkness. You can still make out that we have the interference fringes back. So in the first, so we did a series of 3 experiments. In the first experiment, we had usual Mach-Zehnder interference, behaving as an interferometer. In the second experiment, we put in markers in the two paths. The interference disappeared. In the third experiment, we put in an object after the second beam splitter, which retrieved the interference. So this object is what we call the quantum eraser. So now we will go through this experiment once more with certain explanations as to what is actually happening. Okay? So we go back to the first scenario, where the first scenario doesn't really need an explanation. That's the usual case. And one thing you have to realize is that, you know, we call it a quantum eraser. You would tell me, why am I not doing this with single photons? Well, because it's expensive to bring my photon source here. I don't want to jeopardize the sources in the lab. So we are doing this with a laser because we can actually demonstrate the effect rather well using the laser. But the physics is not the same. Here, this is just a demonstration. But the actual physics is, of course, in the photon case. But the experiment, if done with photons, will have the same results. We'll have to wait for longer for the interference to build up, as you know. Here, of course, you can just see it. So that is the difference. So the actual experiment will be done with photons. It will have the same observations that you're making now. But here, we have demonstrated what is actually happening in the photon case, which is the interesting bit. So here, we have the interference pattern on the wall again. So we might want to zoom in on that. And nothing else. So it's just the Mach-Zehnder. And so this similar interference pattern will also happen in the photon case. So that is simple. Now we will put in Shonchari markers in the two parts. And let us zoom in on the wall again. Right, yeah. So clearly, this is the second observation we made, that we don't have interference. So what is the explanation for this? Now, in this particular case that you're looking at, it is just that we put in, as you noticed, I said, we have a diagonal light. We put in horizontal in one, vertical in the other. So we purposely selected oppositely polarized components which will not show interference to just demonstrate this to you. But in the photon case, of course, what happens is that when the photon is, there's a single particle, it can either go through path A or path B. By putting in markers in the paths, we are actually marking. So we are basically correlating the path with this polarization observation. So essentially, we are marking the path of the photon in this second step and giving ourselves what is called which path information. It is this presence of which path information which actually gets rid of the interference pattern. Because as I said, they won't happen together. So the first was interference, second was which path information. Third, when we put in the polarizer after the beam splitter, again, we might want to zoom in on the interesting thing, which is the interference. So we get back this interference. Of course, somebody might say that this interference is slightly lower in intensity than the beginning one, and that is has a perfectly valid explanation, that we have put in polarizers, which are also absorbers. So essentially, we have less light dealing with. That's all. Nothing more complicated than that. But we gain this interference pattern back. Again, in the classical case, it's rather simple, because we had this H and the V. At the beam splitter. But now we have put in a diagonal. So we're only selecting the same polarization from both sides. And that is what will show interference. So this is a demonstration. But what happens in the photon case, of course, is what forms the principle of this quantum eraser, that we had done this marking in the second step. So we lost the interference, we gained which path information. But now we have done another operation after that. And what happens in quantum mechanics is that when we do something and then follow it up with something else, then the previous information is now scrambled. So now the photon actually, now we don't have that which path information anymore because we've done something else after that, as a result of which we gain back interference. So this is a very interesting quantum effect called the quantum eraser. And of course, there are lots of experiments which have been done on this, called the delayed choice experiment, using entanglement, what happens. Lots of interesting things can happen when you actually bring an entanglement into the picture and so on. But this is our attempt to just demonstrate something to you, and hopefully you will come and also play with it. So I think we will move back to the presentation. So, okay, and of course, the idea is that it's there and you can see it. So, right, so this is what we have, this was the demonstration of the week. I wanted to end with the thank you slide, of course. So then I would like to, thank you for listening to me for a rather long time. And these are all, various visitors who have come to the lab, and Rajesh is missing, but Ashok is here. The community is represented, but you guys should come. And of course, all people here, are welcome to come and have a look. Do tell us before, because most of the time our lab is dark, because we are measuring single photons. So if we have the lights on, then the detector will burn. And it's a very expensive proposition. So then I would like to end on this philosophical note, which I actually personally am very fond of, which is a letter from the son of Max Born that we received after doing this Born rule experiment. So this person is called Gustav Born. He was 5 years old in 1926. Do the calculation. So he's an elderly person. And so he wrote us this letter after the experiment was published, that, how pleased he is that his father, had this theory long time ago, and also got the Nobel Prize, doesn't matter. So look at the humility of great people, They refer to Max Born as their dad. I was very close to him, and I'm so happy that that experiment has been done to prove his theory, and, so this is the idea. So experimental realization, and he is a biomedical scientist, not a physicist, but then, keeps in touch with what is going on with Born rule for sure. And so he wants us to keep him informed, and he's of course still alive, and he wants us to keep him informed, which we did for some of our later work. So we got a letter signed Gustav Born, and that's great, because of course, it's not Max Born, because that would be spooky. But a letter signed Born is very special. We also got a mention from someone called Olivia Newton-John, which again, I'm not sure whether everybody's aware of. She was a very famous movie star, and in a movie called Grease, which is much before many people's time in this audience. But then she's a granddaughter of Max Born's sister. And so then she also said, this experiment has been done. So the point is, this sort of a thing is very important, because as you can see, experiments are not necessarily straightforward. They are time consuming, they take a lot of effort. But then, of course, they result in beautiful science, as well as sometimes acknowledgements from such wonderful people. So on that philosophical note, I would like to inspire all of you to do experiments, also some theory, and then, come and talk to us if you are interested in our work. So thank you very much.
Thanks, Urbasi, for that really fascinating talk. Now, would you be willing to take some questions?
Yeah.
So, first question.
Yes, it is addition of amplitudes.
Addition of amplitude.
That is what, of course, is very important.
Okay.
Yeah,
So
these are
probabilities anyway, the interference is there.
Correct.
Unless it's orthogonal.
So now, in a quantum scenario, we have a complex probability amplitude, as you know. So you have the amplitude and the phase. And so that is what actually leads to this addition and subtraction in rather clever ways towards quantum algorithms. So indeed, yeah.
So is it some kind of nonlinearity or something? Or
No
nonlinearity?
nonlinearity. Sure. Till now, it's very much linear.
So the interference comes in the this thing.
This interference, if you're talking about the IABC, right?
Yeah.
Yeah. The IABC is not the triple slit interference pattern. It is actually the second order interference with sum and difference of triple and double. So it's not the pattern. So it's sum and difference of 7 plus that 8th one I mentioned. Yeah. Thank you.
Any other questions?
Professor.
So where is the sound coming from?
Excuse me.
Okay, yes.
Yeah. Professor, is the requirement of normalization of the qubits a direct corollary of the Euler's identity, because e power I theta is sine theta plus I cos theta, and sine square theta plus cos square theta mod is 1. So, but in the case of sphere, we need to accommodate for steradian instead of radian.
See, sine square. So this is another example where things add up to 1. But then the normalization is very important. So see, you have a qubit, you act on it. It has to remain normalized. That's important, because it has to remain a qubit as it goes along. So normalization condition importance comes from a much more fundamental level than, this is a corollary. This is an example that you've given, but I don't think it's directly correlated to this example. That also happens to satisfy the normalization condition. But here it is very important, because of you have to preserve unitarity. Yeah.
But the range of 0 to 2 pi is only for circle, but you have described it in a sphere, so it should accommodate for the steradian.
No, this is just a representation that, a qubit also has an arbitrary phase. So it's actually alpha 0 plus e to the I theta beta 1. Then you will understand, now you understand, right? So you have a global phase as well as a relative phase between the two terms, which I skipped for simplicity. Then if you take that into account, you can easily derive the equation for the sphere. which I can show you offline. You can derive the blocks here. Yeah. But these phases are important, which I skipped for simplicity. Yeah.
Yes. There was this very intriguing question that I was going through lately. So all the experiments that have been performed with either single photons are like spatially entangled. So I was reading a recent paper where temporal entanglement have been studied experimentally. So I just wanted to know what's the logic behind experimentally performing a temporal entanglement. Like, what would be the idea behind it?
The idea is that, there are different degrees of freedom in which we can harness this entanglement. Right. So depending on, so this will actually be very useful in things like time bin qubits. So, so different degrees of freedom you can manipulate. And then so long as, it depends on what application you want to actually do. So this temporal is going to be crucial if you want to, if you have time as an important parameter in the definition of the qubit.
Exactly.
So you might have read it in the context of a time bin qubit.
Exactly.
So then what happens, so for instance, let me give you an example. So we have the Mach-Zehnder, which now we have understood. So then you have two paths, right? So what sometimes we do is, we make one of the paths really long and the other one short. So then we can easily say that, there is a short path and a long path, and these two define the qubit. So these are the two states. So there, of course, the time stamping becomes important, and the time itself becomes important, because one will take shorter time, the other will take longer.
Okay.
Yeah.
Yes.
So this is very important. So that because we are not doing that, we are doing spatial bin qubits.
Yeah, spatial. Because sometimes what happens in the future of a photon would affect the
so
past of the photon. So that is what I was telling you, that this actually leads to this delayed choice experiment. Exactly.
Yeah. So very interesting discussion one can go on having on that.
Yeah. Thank you.
Yeah, you're most welcome.
Thank you, ma'am. Thank you for the wonderful talk.
Yes.
So I want to know, like, you showed the entangled state of photons, like Bell state and all. So I want to know what is the length scale. So it means how long you can make the system in that state.
That's a good question, actually. So in fact, that is actually related to another problem that we're working on. So that entanglement is, of course, a quantum correlation, but then the system is not isolated. It's actually interacting with some environment, right? So you have things, you can define different types of decay channels, amplitude damping, phase damping, we call them. Without going into details, the entanglement will also deteriorate with time. So entanglement, I didn't go into that, but entanglement, of course, you have to measure. So there are measures of entanglement, like negativity, entanglement entropy, and concurrence, and so on. So you measure that, and let's say concurrence, let's say it's bounded to 1. Now, with time, it will actually drop. So I have to do this because I don't have the corresponding slide. But the point is that this drop actually can happen either asymptotically, which is normal. So it will go to 0 asymptotically. So it will keep on being there, but keep on decreasing, and beyond a point, it will asymptotically approach 0. Or it could happen suddenly. So at a finite time. And this is called the sudden death of entanglement. And in fact, one of the things we are doing is in trying to make the sudden death happen later. So we're manipulating the sudden death time. So in a photon, of course, the time is not a big consideration, because, of course, the decay doesn't happen naturally. You have to simulate it using polarization. But if you think in atomic systems, it could be millisecond, microsecond, and so on. So you have to perform certain operations to hold on to the entanglement. It's a very important area of research. Preserving entanglement, delaying it from dropping to 0, and so on. So, yeah.
So as far as photon qubits are concerned, like, you can get the time, like, as you wish. That's what you're...
No, what the point is that, suppose you consider an atom. An atom has an excited state and a ground state, right? So the excited state will decay to the ground state naturally. You can't do anything about it. That's a natural thing. As you know, we want to, don't remain in the excited state for too long. You come back to the ground state. So there is a time associated with this. So it's e to the minus gamma t, whatever, right? But in a photon case, we define it through H and V, in the polarization, the two states. H won't go to V naturally. Maybe sometimes, some error, it will flip this bit, so to speak. But then generally, H will remain H and V will remain V. So you can simulate, however, H going to V by using certain operations, wave plate operations. And so that is why time is more in your control here. So you can do very nice demonstration experiments of sudden death and delaying them, and basically entanglement dynamics using photons, because time is somewhat within your control. It's more related to the polarization degree of freedom. So, and there's no natural excited ground state.
Thank you.
You're most welcome. Yeah.
Any other questions?
Yes, madam. Please pardon a layperson's ignorance. You had light polarized in two perpendicular directions.
Yeah.
And when you put in the third filter, the diagonal polarizer, where was the possibility of getting polarized light in the diagonal direction?
Yeah,
because it was already polarized into...
Right. So the idea is that, you can actually define, you can actually describe polarization in two orthogonal bases, right? So if I have a diagonal polarization, I can have a component along H and a component along V. So you understand that. That's what we have done. But then the H also can have a component along D and a component along anti-diagonal. So 45 and minus 45. So then, if I actually choose to put a diagonal polarization, I will extract that component from H and the respective component from V. So it's a matter of, it's like a basis choice kind of thing. Yeah.
Excuse me, ma'am.
Where are you speaking from?
Here.
Yes, thank you. Yeah.
Ma'am, you said about doing all these experiments using single photons. So how do you make single photons?
That's why we survive.
Yeah,
so that's what we do. So of course, there are two approaches. So one is, of course, what would seem natural. So you have a laser beam and you keep on putting attenuators there, and then you can make the intensity go further and further down, and you can reach a regime in which you are dealing with very few photons or single. Now a laser beam is called a coherent state. Okay? So it has some probability times 0 photon, some plus some times 1 plus some times 2. That is how you define the state. So essentially, when you dim it down, so to speak, you still are not dealing with a particular, only the single photon. There is a certain probability of that happening. You can make it increase. But you never go down to that true single photon level. But you can still be okay in many experiments using this technique. But if you actually, the most important use of down conversion process, which is what we are doing, comes in when you want entanglement. Because of course, when you have a pair of photons, so here what is happening, you have a strong laser beam. I'm giving you a simplistic description. So you have a strong laser beam, there is a nonlinear crystal, and the polarization is actually, it's a series, so in electric field, okay? So it's chi E plus second order in chi times E1, E2, and so on, okay? So the second order term is what we harness in down conversion. So 1 splits into 2, and of course energy momentum conservation takes a lot of, energy is fine, momentum conservation takes the time. So now here there's a fundamental difference that if you actually do a diagnostic for what kind of source you have, this attenuated one is going to, so again I'm getting into a little bit of jargon, so you have what is called a Hanbury-Brown twist interferometry experiment. You measure a G2 function. So believe me that the G2 function is going to give you a diagnostic of what your source is. So if you use this attenuated laser source, the G2 function will still give you the same curve as a laser. It is going to indicate the coherent state. But if you actually use this sort of down conversion, then it gives you a dip at 0 time delay. So to cut a long story short, the statistics behind these sources are different. And when you, of course, harness entanglement, then you have to do it using our way. Because, of course, then you can zoom in on that cross-section and do several things. The other thing you can do is that, if you are using a photon for an experiment, you lose it, right? So you measure it and it's gone. So here you have a pair of photons which are coming out together. So you keep measuring one and using its partner. This is called heralding. And that is why this is very useful, because then you are using a continuous stream by measuring the other through what is called a coincidence measurement. So that's a rather long answer. Maybe I answered some of your...
Thank you, ma'am.
Urbasi, one question from online. What is a surface plasma? Did you talk about that?
Plasmon.
Plasmon, okay.
Yeah. So essentially, you have some material. Then if you excite it with some electromagnetic... One second. And it leads to the production of these excitation modes. And it's material dependent. So gold actually is amenable to having a lot of these excitation modes, which we call plasmons. So, and we have a video which is not here. Then you can show that, and we actually did the simulation with gold when this paper was released. And you can see that, they actually creep along the surface, and then you can see that the two interact simply because of this production of this in gold and so on. So it is just an excitation mode, I would call it, which is a material phenomenon. I don't know what's... There is some
maybe we will stop the discussion here. We can have... Oh, sorry, one last.
Please.
Yeah, I am asking this question from a layman's perspective.
There's no problem. Those are the tough ones.
Yeah, actually, like whether our observation changes the reality, in the sense being like you told that in the double split experiment, being able to observe a photon, how does it decide whether I am being observed and I should show only 2 bands, and now I am not being observed, now I should be showing multiple bands?
Should I just say that that is one of the mysteries of quantum mechanics? That I don't want to venture into, and so you want to say, there is a book called What is Reality, apparently. Okay, maybe you can find it, but then of course the point is that, you know, this is a philosophical question, it's not a layman's question.
Yeah.
And in fact, you can come up with different implementations of double slit in which you see and not see, and then what happens. I mean, if you actually look up the double slit and what people have tried to do with it, that itself you'll have lots of like-minded people. And I'm also one of them. I'm not really sure of what answer to give, you know, most of the time. I just know what happens.
Okay.
Yeah.
Thank you.
Okay, thanks all. We will stop the discussion here. And of course, there'll be tea outside. You can ask Urbasi again some questions. And there's this experiment here if somebody wants. But be very careful with the instruments. And let's thank the speaker again for this beautiful, wonderful talk.
Thank you very much.